Sketching! All right, we're going to sketch this function. But first, let's break it down. All right, so here's our function. The first question says, where are we increasing and decreasing? Now, in the past, some students have written plus minus graphs as their answer. You will not get credit for a plus minus graph. A plus minus graph counts as work. It does not count as your answer. Okay, so the first thing we got to do is we got to take the derivative so that we can find out where our critical values are. Our critical values are at positive 2 and negative 1. So I put my positive 2 and negative 1 on a plus minus graph, and then I do my tester points. I have a negative 2, 0, and a 3. You can pick any number in those intervals. Doesn't matter. And then most of the time when you do that, you can do the math in your head. So you take the negative 2 and plug it in right here. And right here, and see if you get a positive or negative result. So if I plug a negative 2 in right here, then this would be a negative number. If I plug a negative 2 in right here, then this would also be a negative number. So we have a positive number times a negative number times a negative number, which would be a positive. And so I have a positive right here. Boom. Now you do the same thing with each of those other points. You get your other signs, and now you know where the function is increasing and where the function, that's f, is decreasing. And so I write my answers. We are increasing from negative infinity to negative 1, and then from 2 to positive infinity. So that's this interval and this interval, because this one starts at negative infinity, and this one right here ends at positive infinity. And then we have our decreasing from negative 1 to positive 2. That's it. Next, identify any local extrema for the function. Now, because it doesn't say relative extrema, I am going to assume that it's talking about absolute extrema. Okay, now in my answer, I was a little thorough, but you don't need this part. That's why I put the X right there. This is the part that you need. There's no absolute extrema, and the reason why there's no absolute extrema is because this is an odd function. You could talk about end behavior, but just stating that it's an odd function is enough. What's an odd function? Well, this is an even function. When you have an even function, it points in the same direction on the endpoints. An odd function points in the opposite directions, okay? So if we have an arrow pointing down and an arrow pointing up, that means we cannot have an absolute max or an absolute min unless we have endpoints, and then in which case it would stop the function. So that's all you have to say here. It's probably just worth one check mark. Here I did talk about, just for funsies, what a local max, or where local maxes and local mins are. And so just pay attention to the explanations, because so right here I say at x equals negative 1, there's a local max. Why? Because f prime is greater than 0, then f prime is less than 0. That's why. At x equals 2, there is a local min because we would be negative than positive, right? So f prime is less than 0, then f prime is greater than 0. So just pay attention to those. That's how you would justify your results if it asked for relative extrema, relative or local extrema. On which intervals is the function concave up? So here we need our f double prime. We need a second derivative. We've been using plus minus graphs, so that's what I did. I took the second derivative. I set it equal to 0, and then I solved it. I got 1/2. I put 1/2 right there. I have 2 tester points. When I plug in my 2 tester points, I get minus and plus. Therefore, we are concaving up from 1/2 to positive infinity, which is what I have right here. On 1/2 to positive infinity, f is concave up because f double prime is greater than 0. It doesn't even ask for the explanation, but I still put it there just out of habit, I guess. Identify any inflection points for the function, justify your results. So here we can say that x equals 1/2 is an inflection point because f double prime is less than 0, then f double prime is greater than 0. What you want to do is you want to say that the sign changed, the concavity changed at 1/2. Therefore, it is an inflection point. All right, so now we're going to sketch the function. I draw these dotted lines everywhere I have a critical value and everywhere I have a possible inflection point. Okay, so if I go back up, I have a 1/2. And I have a negative 1 and a positive 2. So negative 1 is right here. There's my 1/2, and there's my positive 2. So I drew a dotted line on each of those because one of the signs changes. Okay, so this is my f prime, And this is, ooh, what a funky F. And that's my F double prime right there. So, all right. So what about the points? Ooh, that's a good question. We don't know any points except for this one. This one is just too obvious. You got to put a -5 y-intercept point right there. That is way too obvious. You must have that. You can find more points, but I'm not going to be too picky about the other points. Just this really obvious point, because all you have to do is plug in 0 to x and you would see -5. All right, I don't care about the other points very much. Not even the x-intercepts. Only if they're given to you, all right, which they're not given to you. I care only right now for my FRQs. I only care about the curvature of our lines. Are you increasing and concaving down correctly? Are you decreasing concaving down? And then let's see, to there, and then our concavity changes even though we're still decreasing. And then here we're increasing, concaving up. And that's the way your graph is supposed to look.